rise again, right? So we are interested in that second route where this curve flows across the x-axis at 0, right? So because we know if you take the second derivative, I mean, this is greater than 0, so the function is convex. So we covered all this stuff here, if you remember, and then we say this is the nature of the function which we are going to have. This is our a. So it is going to start from 0, and then it will go like this one here, and then it will cross the x-axis at this point here, right? So this is our adjustment coefficient, right? Yeah, so if you don't worry much about that, then I think what is important, so we proved this one here. I said, of course, you can expect the upper bound for R. I don't think if this is very useful anyway, but we proved this here by using the Maclaurin series. If you remember, we said, of course, here we're going to have the inequality, and the reason we're going to have inequality is because we are truncating this series. We're not going on and on and on, because remember this series, if you remember, the Maclaurin series, if you expand this one here, it will go up to infinity, I think, if I'm not mistaken. So if you truncate it, it means that now this part here will not be equal to this part here, right? It means that this part here will be greater, right? Before it was equal, but since we are truncating this part here, then we are going to have something which is greater than what we had before. That is why we are saying this here will be greater or equal to. So we proved that thing, and then we ended, and then we said, okay, this is the upper bound for R. So I want to start from here. So we have some few things, of course, which we have to cover. So unless if you have any question while I'm moving, so I'll just move from my desktop, and then I'm going to move to yeah. So if you have any question, I think it's a good time now to ask. So just so does that make sense? Or maybe it's confusing. So does that make sense or not? Okay, so does that make sense or it doesn't? Okay, thank you, Ali. Yeah, no worries. Unlike Dallas, I don't give feedback. So let us move like this. So is up to you, see. So if you don't respond, then I don't think if that is a problem to me. So let us move on. Um, uh, okay, so I just want to prove the other thing in this part here, because if you remember, we have also this part here. So we have this part here also we have to prove. So we have proved this part here, right? But proving the second one, I think is straightforward. Why? Because so this is proof two. And in proof two, of course, since we know R is less or equal to 2, and then C minus lambda, and then M1 divided by lambda M2. Of course, what do we have to do now to arrive at that, to arrive at that second inequality is actually to define the premium, right, of what I've done with my camera. Sorry, 1 second. I don't know what I've done here. Okay, so something strange here, right? Mm, Sorry. What is happening here? So, I don't know what is happening to my external camera. So just 1 second. Yeah, we are using external camera. So why is okay? So I think it's okay now. So what I was saying now here is that I think here is straightforward, because what you have to do now is you have to say what And then now C is simply the pure premium, right? So it's simply C and then plus theta. And then of course you have multiplied by lambda, lambda M1. So lambda M1. So I'm using this here from this. So this is what we have to use in order to prove that, right? So this is, I think this is too bold maybe, or maybe no, not. So of course this is equal, right? So what I'm going to do now here is simply to substitute this part here. So of course you can just put it here, and then you're going to end up with something like, so R will be less or equal to 2, and then you're going to have 1 plus theta, and then of course lambda, and then M1, and then it might subtract M1, and then of course divided by lambda M2. So what we can do here now, right? Because we know this part here, everything will go. So we're going to remain with theta lambda M1, right? And then of course divided by lambda M2. So if you simplify this, you'll get, I think, 2 out, and then you're going to remain with so theta M1, and then divided by M2, right? So this is actually what you're going to get. Okay. So yeah, I think I asked this question probably in the final exam last year. And I don't remember the feedback, but because I did not mark it. But probably, I mean, majority of students did well anyway. So I think I can show you this simple question. So final exam, final exam, master. Okay, so where is it? Okay, the allocated courses, academic year is last year, and then second year, and then we had the exam, final exam. So I'm checking that question, and then of course the final exam, right? Just want to show you this question. So it was a very simple question. I don't remember anyway. But I think majority did well in that question. I think I gave them. So you can see here, where is it? Yeah, I think it's here, right? So it was very simple. So what I did, I asked them, okay, where is it? Where is it? Oh, this one here, right? So it was I think the second lecture anyway. But you can see the question, claim on a portfolio of insurance policies alive according to a Poisson process with parameter lambda, claims the amount having a normal distribution, and there is loading factor of theta on premium. The insurance has an initial reserve of initial surplus of U, study the 4 factors that affect the size of this. You should be able to answer this one here because you have we know the process is affected by the claims amount, initial surplus. You have what you have to, so the initial reserve, the premiums, and what you have to pay out, right? And then, of course, briefly explain for each factor, what happened. Okay. So I think in the next lecture, anyway, I think I mixed this thing. But you can see the way we are stating this one here, should be surplus process. So all the question you're going to get will be Poisson, right? We're going to make an assumption about the Poisson distribution, Poisson distribution, Poisson distribution. And you can see, of course, you have to prove this relation here. Right. So this I will cover this one here next week. I remember when I was teaching this part, yeah, I asked them, do you think there is an arbitrage opportunity in this scenario? And yeah, and then I asked them in the exam, and then they will answer this question, right? But you can see, I mean, the nature of the questions. I mean, I think the questions will be straightforward, similar to this one here. Anyway, this will be the part of oh, hivi nilikuwa naonyesha kwenye desktop anyway. Oh, sorry for that. I thought nime share this thing, but yeah, no worries. I will show you maybe at the end of this one here. Yeah, so sorry for that. I thought naonyesha screen nyingine kumbe natumia screen. Okay. No, I cannot send all the past exams, right? Ismail, I cannot send all the final exams. I don't want you to focus on the questions. Kwa sababu nikiwapa final exam mage mta you have all the exams. I can share the yeah. Sharing sharing the exam, the reason why I don't want to share the exams and maybe the solutions is because there is a difference between finding something and of course I have all the exams and the solutions. But the problem with doing that ni kwamba you is different. If you have access to everything and if you are looking for something, unavyotafuta something, I mean, I'm more likely utakutana na vitu vipya vingi zaidi kuliko kama nikikupa everything and then everything is there, right? So that is why I don't like, I mean, to give you all the exams and the solutions. Because in the process of finding the solutions, you'll be able to discover more and more and more compared to me nikupa everything, the solutions and everything are there. Ni vitu vili tofauti kabisa. So that is why actually we don't share I mean the marking guide and stuff like that. But for the final exam is not me. So the final exam is the university policy. Ndio, kwa sababu you have to submit the final exam at the end of the day. And the argument was student wana concentrate sana kwenye past exams. And I mean they focus on final exams. Kwa sababu sisi zamani tulikuwa na access na final exams za zamani. Kwa sababu tulikuwa natoka nazo, lakini whether I agree with that or not, I mean, I think is irrelevant. But I think the point is not more of us. But I cannot share the final exam. I can share the test or the test if you want. Nadhani na test chache tu, maybe na miaka iliyopita huko mingine, lakini currently I think I just have one test ambao probably I mean you have access to it. I can share the quiz, I can share everything. But the final exam I think is university police, right? I mean, is not me. Yeah, ndo maana hamtoki na final exam, sio? Zamani tulikuwa tunatoka na final exam, nowadays we don't. Kwa nowadays ni ubaya. Yes, yeah, kwa mtu kasema kwamba definition ya kula kwa jasho. Yes, yeah. Nowadays ni ubaya tu, sio? Yeah, but that is not me. I mean, it's university police. Yeah. Yeah. So this was, I think, I mean, it's straightforward. And what we have to do now is simply we have to prove the upper bound for the probability of ruin. I think this is more important now because at the end of the day, we were interested in the probability of ruin, right? ISO adjustment coefficient. Of course, we have to estimate the adjustment coefficient because we are going to need the adjustment coefficient to estimate the upper bound probability of ruin. But what is important now is actually what we are going to cover here, right? So of course, we have a theory about this probability of ruin. But I just want to I mean, demonstrate this one quickly, right? So I'm going to use, I mean, the same idea about about the moment generating function, which we had before. So if you remember, we said we can rearrange our equation, right? So we said, suppose this one here is I mean, is the either. Of course, this makes sense because I'm taking the exponent of r and then I'm multiplying it with the surplus process. So of course, if we do that, then what I've done here is simply to define the surplus process, right? So these two sides, of course, are equal. So I've just, I mean, expanded what we had before, right? But we know this here is actually the moment. So if you take the expectation of that part is simply the moment of the surplus process, right? So if you simplify that, of course, you can rearrange all the stuff, and then you're going to end up with something like this one here, right? So probably what is interesting in this part here now is just like the idea which we had before. So I'm going to substitute this part here because we know if we have I mean, a Poisson distribution, then of course we can define the moment in this way here. So kama ukumbuki refer to the lecture which we covered before about aggregated claims. So then of course you can simplify everything. So now you'll end up with this part here. But now we know, right? We know the relation between the premiums, the relation between C, and we can rearrange this equation further because we know that from the adjustment equation, then this equation here should hold. So these two parts here should be equal, right? And then of course you can rearrange further this one here, and then if you substitute that, of course you're going to end up with something like this one here. And this one actually makes sense because it's the same thing. it's almost the same thing like what we had before, because we said we have to remove that part, and then we say that part is actually the adjustment equation. So what value is going to give us 0 is when we is actually what we call the adjustment coefficient. So we said if we substitute the adjustment coefficient, the entire part is going to be 0, right? So it's like you are going back to that idea before. And if you do that, of course, this is actually what you're going to remain with, right? So this is actually what you will end up with at the end of the day if we do that kind of manipulation. But the same thing, just saying, if I have the adjustment coefficient called R, if I substitute back to the expression we had before, what am I going to end up with? Of course, I'm not going to end up with T, because we don't want this process to explode at the end of the day. So we're going to end up with something like that one, right? Of course, I will not ask you to prove this thing, but I just want to understand maybe where this thing comes from, right? Of course, we'll see even in the source. I mean, they're not proving this stuff, right? But probably, I mean, it should make more sense now. Because last year I did not put this in the lecture, and nilikuwa na question where that comes from and stuff like that, right? And then, of course, you can apply the Markov inequality. I don't expect you, so I'll not assess you about this one here, but you can see now, if you know this part here, you can use the idea from, you can borrow the idea from Markov inequality, and then of course you can show that, because if you have the infimum, given that t is greater or equal to 0 of this part here, this is the same as writing the supremum of the exponent of what we had before, right? So anyway, I will not cover this part here, but at the end of the day, we're going to end up with this probability here. So this probability is what we call the upper bound for the probability of ruin, because if you remember, this is the symbol for ultimate ruin, right? So ultimate ruin, of course, can be estimated from this Markov inequality, and then we end up with this one here. So this is what we call the Landberg inequality. In the source, we have a theorem, and this theorem it may state this and this and this, right? And then applying, of course, the Markov and then the Landberg inequality, you end up with the ultimate probability of ruin, which is given by this one here, right? So what you have to understand in this case here is simply the upper bound for the probability of ruin. I will not ask you to prove this. So of course you have this definition now that the Landberg inequality, that the probability of ruin, the upper bound for the probability of ruin, is simply given by this part here, right? Of course, we know R, so R is actually the adjustment coefficient, which we need, I mean, in order to make that part, if you remember, the adjustment function to be equal to 0. So of course, you can put this one here, right? So what we are saying in this part here, we cannot get the exact formula for the probability of ruin, but we can have the upper bound. So what we are seeing in this part here, this blue part here, this one is the upper bound. Sindio, kwamba is the upper bound. Kwamba the probability of ruin, we know that it cannot go beyond this part here. So ideally, what we are saying ni kwamba probability of ruin ambao utaiestimate itakuwa somehow below that part, right? It can be that part, it can be maybe here, it can be maybe here. We don't know where it's going to be, but we know that it cannot go beyond that upper bound, right? So the blue part is actually the upper bound, and of course the true ruin probability is actually denoted by the dotted red added line. Sindio? That is the limitation we have now. Of course, kwamba we don't have a formula, right? But if you go and practice, I mean, you have all these powerful machines nowadays. I mean, you can simply estimate that kwa kutumia numerical methods. But we are not covering numerical method in this course, so I cannot ask you a question, okay, maybe find the probability of ruin given that you have this and this, right? I will ask you a question, find the upper bound for the probability of ruin. But exactly the probability of ruin, of course, you need to use numerical methods, which is beyond, I mean, what we have to cover in this course. So it's very simple. In case kama ukiulizwa swali la ruin, itakuwa ni swali kuhusu estimate the upper bound. Ambayo is very simple, is simply E minus RU. Where R, I mean, is simply the adjustment coefficient. So maybe kazi itakuwa ni estimate the adjustment coefficient. Once you get the adjustment coefficient, of course, you can estimate the probability of ruin there. So here, just, I mean, the comment, of course, at the end of the day, R is a function of the parameter that affect the probability of ruin. So, R behavior as a function of this parameter can be observed, premium loading factor variance. Okay, so at the end of the day now, the probability of ruin right, will depend on these factors here, the premium loading factors, the variance of the underlying claims, distribution, and stuff like that. And I don't know, this should be obvious because the probability of ruin now, it will depend on the premium loading factor, right? So we expect the higher the higher the loading factor, right? Then of course, probably, I mean, we're going to observe low probability of ruin, right? And if the variance of the underlying claims distribution, let's say, is low, right? Of course, we can predict that. So we expect if the variance, I mean, is low, right? Of course, we expect the probability of ruin to be low as well, right? But if, I mean, the variability of the underlying claims, if the variability of the underlying claims is large, right? You know the problem with the variance, right? So the higher the variability, of course, the higher the probability of ruin. But if why? Because you cannot predict that with certainty. And the lower the variability of the claims, of course, the lower the probability of ruin. So that is what we actually expect. So next time ukiulizwa swali kwamba what are the factors ambazo zina affect probability of ruin, I think I showed you in this exam, sababu ndo swali ambalo lilikuwa hapa. I think it should be straightforward thing, right? Where is this? Sorry. So for an exam, yeah, so this is what I was asking you here, right? Okay, so where is that question? Sianze kuangalia maswali hapa mkazani nitarudia the same questions. So briefly explain for each factor what happens to this one here when the factor increases, right? So 34 factors that affect the size of this. So this is the probability of ruin, right? I mean, it does not matter because it's simply the probability of ruin. This is the ultimate ruin, but it's bounded, right? We discussed this one here on Wednesday, right? But we are saying you can have, let's say, the premiums, or you can have maybe the cost, you can have things like that, right? So the question was, okay, briefly explain for each factor what happened to this one here when the factors increases. So we are saying what happened if, I mean, let's say, anyway, najisahau bado. Thank you for reminding me, Ismail, anyway. Sorry for that. Yaani nachanganya screen, sorry for that. Kwa sababu na view kwa kutumia nyingine afu natumia nyingine. Anyway, so let me finalize with this question. Sababu I told you tuna small part too. So I'll just demonstrate by using this question. I think it's a simple question because we have an insurer knows from past experience that the number of claims received per month is a Poisson distribution, right? So the first thing is this one here. Kwa sababu the entire lecture toka tumeanza ni kwamba we are making an assumption that we have a compound Poisson process, right? And if you have a compound Poisson, it means that we are making an assumption that we have the number of claims follows a Poisson distribution, right? Ukishaona nimeandika kwamba let's say it follow a binomial distribution. I mean, everything does not make any sense. Ile adjustment equation is no longer like that, right? Ile adjustment equation iko vile kwa sababu we are making an assumption that we have a Poisson distribution for the number of claims, right? So utaona maswali yote na Poisson. The moment you assume other distribution, so everything will change, right? And probably you're not going to have closed form or maybe like equations which are straightforward like what we have for the Poisson distribution. So of course, you know the meaning of this Poisson distribution, right? And that the claims amount have an exponential distribution, which means this one here, right? So you have two things here. You have the number. So you know the number follows a Poisson distribution, right? And then you have the x. So the x in this particular, it follows an exponential distribution. So in the core, you have these two distributions here. So the insurer uses security loading of 30%, right? So security loading, we are saying, okay, theta is equal to 30% in this part here, right? So security loading in this part here, you look at your expenses and you ask yourself, okay, what profit do I need? Kwa sababu you are doing business, kwa maana yake hiyo inatakiwa capture profit, all the expenses you are incurring, si ndio? Kwa 30% is actually the security loading, si ndio? You will get some profit, you will be able to cover some expenses and stuff like that. So insurance company na believe kwamba ikiseti this loading 30%, then that makes sense, right? Of course, I mean, this is empirical question. Manake insurance company, they have to do empirical analysis to arrive at this point here, si ndio? How ukienda kufanya kazi kwenye serious insurance company, you'll be doing this stuff, right? Ukienda kufanya kazi kwenye insurance company za Kariakoo, then of course you not see this one anywhere, si ndio? Kwa sababu utakuta tu zile premium wamekuletea pale kutoka sijui Tira huko, sio? Kwa you just have to apply. Yo, kama gari ni hapa tu hapa, hapa tu hapa, then charge this, charge this, charge this, si ndio? Call like that, sio? But if you'll be doing this, I mean, of course, in serious setting, of course, we'll be able to see how we can estimate all these loadings. And then, of course, calculate the insurer adjustment coefficient and give the upper bound for the probability of fraud. So you can see the question is asking to estimate the adjustment coefficient. And we said the adjustment coefficient is what we call it R. And then, of course, give the upper bound. So the upper bound, we know the formula is very simple, right? So that is actually what we have to do in this part, right? So we have a Poisson process. And if we have a Poisson process, we know it's very easy because we know that the adjustment coefficient is given by mx and then r and then minus lambda and then of course we have cr, you have minus CR, and this one is equal to 0, right? But we said we can have a more simple form in this part here if we define C, because we know C is 1 plus theta, where theta is the loading factor, and then we multiply with lambda M1, where lambda M1 is actually the pure cost. Sindio is in the aggregated claims. Sindio, this is the pure cost. You can estimate C by using that formula. Sindio. Okay, so if we substitute this C here, of course, the formula itakuwa more simplified. Tuliona kwamba if you do that, you'll end up with a very simple formula ambayo inasema, I don't know if you remember, lakini I think in mxr is equal to 1 plus theta, and then of course I think m1. Sindio, okay, simplify that thing. You can see now we have a very simple form. Kama nakumbuka, I think we proved this at some point. We proved this one here at some point, not here. Yeah, we showed that. No, not here. I think we proved this one here at some point. Yeah, here. Oh, I forgot one. So you can see that mx of r has got 1, and then plus this 1 plus theta, and then m1r. One, yeah. So we are going to have here, of course, you will be able to prove that nadhani, or you will be able to see. Kwa I forgot here, kuna term nimeisahau hapa, sorry. So we're going to have this one here is equal to 1 plus theta, and then of course we have m1, right? So this is what you are going to have. Then because we have everything, so I think what you have to remember ni kwamba this moment here, any moment ya x, kwa sababu remember you have two distribution. You have the number, and then you have the claims amount. So don't confuse the thing. So to me, a moment ya Poisson distribution. Here we are interested in the moment of the exponential distribution. Why? Because we have been told that claims amount have an exponential distribution with mean this one here. So you have, let's say, a Poisson with parameter lambda, and maybe I have an exponential, let's say, with parameter beta, right? So just remember that. So because we know, right, I know the moment if I have an exponential distribution. Of course, you can check that. It will be given in the exam, but the moment I think is same. I think is beta divided by beta, and then minus r. This is the moment of an exponential distribution. So this one here should be equal to 1 plus theta, right? And then, of course, m1. So here you can see that what is m1? M1 is simply the first moment, right? So it's the expected value of x. Right? So you know the mean of x, right? So what is the mean? The mean is already given. So you can see it's very simple because now we simply need to substitute what is beta. What is this one here? Of course, you can see here, kwamba tumepewa, this is an exponential distribution. The mean exponential distribution, the mean of x in this part here ni tumepewa ngapi? Tumepewa 500. So we have 500 in this part here. So now you can see that this is very easy now. So the expected value of x is equal to 500. So of course we know that the parameter, kwa sababu we know the mean is 1 over beta is equal to 500. So you can see now here you can simply substitute everything. Remember you have this one here as well. So you have the theta. So the theta is 30%. So this one is 30%, right? And then of course you have the mean. So the mean is 500. So you can simplify everything. So I'll just give you the final answers. Of course you can solve this. So I'll simplify now. So if you do that, I think you'll get the adjustment coefficient. R should be equal to 0.000 and then 462. So this is the adjustment coefficient. And once you get the adjustment coefficient, remember the second question asks you calculate the adjustment coefficient and give the upper bound for the insurer probability of ruin, right? If the insurer set aside an initial reserve of this one here. So initial subprice or initial reserve is actually the same thing. So this is actually your U, right? So what you have to do now, I think, is very easy. So what you can do now is that then the upper bound for the probability of ruin, right? Remember, probability of ruin cannot go beyond E minus R and then minus U, power RU. So this will be less or equal to E. Remember, you have what is R. R is this one here, 0.000462, and then multiply by U. So remember, U is actually 1,000. So just multiply here by 1,000, right? 1,000. And then, of course, you are done. So if you do that, you'll be able to see that the upper bound for probability of ruin is actually 0. This one here, right? So probability of ruin cannot go beyond this part. Okay. So I think it's just a straightforward question. So you can see, I think what is important is understand what is an adjustment equation. But this one here is an adjustment coefficient under the Poisson framework. And over the entire lecture, we have assumed that we have, this Poisson distribution. And also understand how we can explain the probability of ruin, which is simply E power minus RU, right? I will not ask you how to derive the upper bound for the probability of ruin. I will not ask you to derive the adjustment coefficient, the subprice equation. I cannot ask you to do that, but I can ask you to define what is the subprice equation. So I will end here, right? I hope sijachukua dakika nyingi sana mbele, lakini I think this is enough. So you can go now, but if you want to see that question ambayo nilikuwa naionyesha, if you have some time, I can show you, but it's not important and it's not part of the lecture. So unless kama kuna swali up to that point. So any question? Any question? So next week I will actually continue from where we ended. I think kwa sababu topic sio ndefu sana, lakini we have the other part I think which is also very important. Na according to my assessment, I think it's somehow challenging according to my observation from other years, simply kwa sababu ni topic za mwisho. Of topic za mwisho, it seems like you don't pay attention. That is my assessment, I think. You don't pay attention na zikija kwenye mtihani then inakuwa ni somehow challenging. Yeah, so I think you can see my screen now. So I think I was talking about this question. So I think you can see it now. You can see I gave the same question anyway. You can see niliuliza hili swali last year. The same question from the lecture. Same question from the lecture. It's all about how to solve sasa hivi, si ndio? It's the same question. I think wanafunzi walifanya vizuri anyway. I did not mark this question, but I think they did well. This question is an example. Mtu aliyekosa yani is like so these are the questions which I typically give for student to just get the marks. Kwa ukikosa manake that is beyond repair. We cannot repair you. And then of course you can see this is what I was saying, that claims on a portfolio of insurance policies arrive as a Poisson process with parameter lambda, and the claims amount having a normal distribution with mean, mu, and variance, this one here. And there is a loading theta on premiums. You can see all these questions here. We are showing a Poisson distribution, right, for the number, right? Why? Because at some point, probably have to use the adjustment equation, and we have to align with what we have covered. The moment nikitwist to this question here, nikiweka distribution nyingine, that adjustment equation does not apply anymore. So this is what I will cover next week. Because next week now we have to think about what if we incorporate the reinsurance arrangement. Because today we are making a very simple assumption kwamba we just have the claims. We have not taken into account the insurance policies. So now we are saying, okay, what if now we take into account the insurance policies? So you can see this cause, it's simply just extending stuff, moving from the basic to some extension, right? So you can see here the question was 34 factors that affected the size of probability of ruin. And this one is bounded between 0 and t. So state the factor affecting the size of probability of ruin. This should be straightforward, because connection kati ya yeah, 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 probability of ruin and then the adjustment coefficient, right? And then you have to think about the adjustment coefficient itself. Sindio? Adjustment coefficient, if you are careful, kwamba adjustment coefficient ni E and then minus U and then you have R, right? So now what is R? Adjustment coefficient. So U is the initial reserve. So think about how initial reserve affected the probability of ruin. Because if you have higher initial reserve, of course, if you keep the adjustment coefficient constant, probability of ruin will go down. It's an exponential. So that should be obvious. Initial reserve. Think about the premiums. Think about the claims amount, right? Think about the variance. Think about the loading factors, right? So factors ni nyingi, and this I think you are supposed to mention uh, yeah. Na maswali kama haya nakupa quota mark, right? Of course, kama umemention tu initial reserve, I think 0.25 is enough. And of course, you have to explain anyway how does that relate to that. But just go straight forward to the point kwa sababu huwa natoa this instruction. I don't know if huwa mnafollow kwamba please just go straight forward to the point. Nobody cares. Nobody cares how long your paragraph is. Just